Welcome to all of you. Now we discuss Unit 3, Group B, 2023 Biomathematics, Semester 5 Mathematics Honors, University of Calcutta. The question paper 2023 Unit 3, Question 8a. Suppose X star is a steady state of the system xn plus 1 equal to fxn, where fx is a continuously differentiable function and modulus f dash x star not equal to 1. Prove that x star is asymptotically stable if modulus f dash x star is less than 1 and unstable if modulus f dash x star greater than 1. Consider the first order nonlinear difference equation xn plus 1 equal to fxn. Let x star be a steady state of the system 1. Then xn plus 1 equal to xn equal to x star. From 1, x star equal to fx star, because xn plus 1 equal to x star, xn equal to x star. If x star be a steady state, then x star equal to f of x star. To study the stability of x star, we set xn equal to x star plus un, where un, that is equal to xn minus x star, is a small perturbation about x star. Using 3 from 1, we get this x star plus un plus 1 in place of xn plus 1. This equal to f of x star plus un by 3. Expanding by Taylor's expansion about x star, this is equal to f x star plus un f dash x star plus order of un square. This is approximately equal to f x star plus un f dash x star, neglecting u square and higher order terms as un is small quantity. So this fx star equal to x star by 2 plus un f dash x star. Cancel x star from both sides, so we get un plus 1 equal to un f dash x star. Equation 4. Here we assume that fx is continuously differentiable function on an open interval I containing x star and f dash x star not equal to 1. Equation 4 is known as linear approximation of the nonlinear equation 1. This given equation xn plus 1 equal to fxn, this is the nonlinear equation, difference equation. So corresponding linear approximation is given by 4. Now modulus of f dash x star equal to modulus of un plus 1 by un from 4. Case 1, when modulus of f dash x star is greater than 1, then obviously modulus of un plus 1 by un is greater than 1, that is modulus of un plus 1 greater than modulus of un. So un will not approach 0 and consequently xn will not approach x star, because here un plus 1, modulus of un plus 1 is greater value. So un will not approach 0. Then xn will move away from the equilibrium point x star as time increases, and x star is said to be an unstable equilibrium. Case 2, when modulus of f dash x star is less than 1, then modulus of un plus 1 by un is less than 1, that is modulus of un plus 1 is less than modulus of un. So un approaches 0 and then xn will approach x star. X star is said to be a locally asymptotically stable equilibrium. Note that there is exponential convergence if 0 less than f dash x less than 1 and oscillatory convergence if -1 less than f dash x less than 0. And note 2, these criteria are sufficient but not necessary, because if this x star is asymptotically stable if this hold less than 1, but if x star is asymptotically stable, not necessarily that modulus of f dash x star is less than 1. Does not imply modulus of f dash x star less than 1 if this is asymptotically stable. If this modulus of f dash x star is less than 1, then x star is asymptotically stable. But conversely, if x star is asymptotically stable, does not imply that modulus of f dash x star less than 1, and unstable is for this. Next question part B. Discuss the stability of each steady state of the system xn plus 1 equal to 3xn by 2 plus xn using cobweb diagram with initial value x0. Show at least 3 iterations in each case. Here the system is given by xn plus 1 equal to 3xn whole divided by 2 plus xn. If x star be a fixed point or steady state, then xn plus 1 equal to xn equal to x star. So we can put x star in place of xn plus 1 and x star in place of xn from 1. So we get x star equal to 3x star whole divided by 2 plus x star. So after simplification, we get x star equal to either 0 or x star equal to 1. So there are two steady states, x1 star equal to 0 and x2 star equal to 1. To draw cobweb diagram, put xn plus 1 equal to y and xn equal to x. Then 1 becomes this y equal to 3x whole divided by 2 plus x. So by Desmos application or other, first we draw this y equal to 3x by 2 plus x. This is the curve, reproduction curve. This y equal to 3x whole divided by 2 plus x. Next we draw the line y equal to x. The intersecting points, this 0 0 and this 1 1. So we get the two steady states, x1 equal to 0, here x1 equal to 0, y equal to 0, this x1 star equal to 0, and from this point this x2 star equal to 1. So intersecting point give the two steady states, x1 star equal to 0, x2 star equal to 1. From cobweb diagram figure 1, x1 star is an unstable fixed point, because if we choose x0 is here, so from x0 to this reproduction curve, then from this point reproduction curve to draw a parallel line to the x-axis, this line, and from this the vertical line, draw vertical line up to reproduction curve, then horizontal line parallel to this x-axis, this up to y equal to x line, and so on. So this corresponding solution approximation x0, x1, x2 move away from these steady states x1 star equal to 0. So here x1 star is unstable, as the solution points x0, x1, x2, this x0, this point x1, this point x2 move away from the steady state x1 star equal to 0. So this is unstable, x1 star equal to 0 is unstable. Next, from figure 2, x2 star, if we choose x0 is here, so we draw this point cobweb webbing diagram. This asymptotically stable because these solutions x0, x1, x2 move closer to the steady state x1 star, x2 star equal to 1 along x-axis. This is the x2 star equal to 1, this point is x2 star equal to 1. So we see that x2 star equal to 1 is locally asymptotically stable. Next question 9a. Consider the discrete time predator prey system xn plus 1 equal to axn bracket 1 minus xn minus bxn yn and yn plus 1 equal to minus cyn plus dxn yn, where a, b, c, d are positive parameters. Find the steady states of the system and discuss their stability. Let x star comma y star, this point be a steady state. Then xn plus 1 equal to xn equal to x star and yn plus 1 equal to yn equal to y star. So put xn plus 1 equal to x star and xn equal to x star in the first equation, and yn plus 1 equal to y star, yn equal to also y star in the second equation, and this system, and solving this system x star equal to this, from 1 we get this, so either x star equal to 0 or ax star plus bx star equal to a minus 1, and from the second equation this y star equal to this, we get either y star equal to 0 or dx star equal to 1 plus c. Equation 4. If we choose x star equal to 0 from 3, then y star equal to 0 from 4, so x star y star equal to 0 0, this is equal to e0 say. Next we choose y star equal to 0 from 4 and put y star equal to 0 here in second equation of 3, then we get x star equal to this a minus 1 by a. So another steady state x star y star equal to a minus 1 by a comma 0, this is called this e1 say. Next choose from the second equation of 4 this x star equal to 1 plus c by d, and put this x star here second equation of 3 x star, and we get the value of y star is this, this y star equal to this, so x star y star equal to 1 plus c by d comma d bracket a minus 1 minus a bracket 1 plus c whole divided by b d equal to e star c. So there are three steady states: e naught equal to 0 comma 0, e1 equal to a minus 1 by a comma 0, and e star equal to 1 plus c by d comma and this. Now for feasibility of e1, that is biologically meaningful for e1, we must have this a minus 1 greater than 0, so a is greater than 1, and for feasibility of e star we must have this d into bracket a minus 1 minus a into bracket 1 plus c must be greater than 0. That is if a minus 1 by a greater than 1 plus c by d. Now we find Jacobian matrix J for this system. Let xn plus 1 equal to f xn yn and yn plus 1 equal to g xn yn, where f xn yn equal to f xy, put here xn equal to x and yn equal to y equal to ax bracket 1 minus x minus bxy. From the given system is this, so right hand side is called fxy and left and for this gxy for the right hand side. Next del f del x, del f del y, del g del x and del g del y, we get this. Hence Jacobian is this fx fy gx gy. So we get a bracket 1 minus 2x minus by minus bx dy dx minus c. Now stability analysis for this steady state e naught is equal to 0 comma 0. Put here x equal to 0 and y equal to 0, here we get this Jacobian at this point e naught is a 0 0 minus c. The eigenvalues are lambda 1 is equal to a and lambda 2 equal to minus c. Hence the steady state e naught is asymptotically stable if modulus of lambda 1 that is equal to modulus of A is less than 1 and modulus of lambda 2 that is modulus of C is less than 1. Since A and C are both positive, hence E naught is asymptotically stable if A is less than 1 and C is less than 1. This is the condition for asymptotically stable, locally asymptotically stable for this steady state E naught. Next, for this point E1, steady state E1 is equal to A minus 1 by A comma 0, where A1 must be greater than 1. The Jacobian J for this point E1 when x equal to A minus 1 by A and y equal to 0 put here. So we get 2 minus A minus B bracket A minus 1 by A 0 D bracket A minus 1 by A minus C. This is the upper triangular matrix. So eigenvalues are this lambda 1 equal to 2 minus A and lambda 2 equal to D into bracket A minus 1 by A minus C. For locally asymptotically stable of the steady state U1, we must have modulus of lambda 1 is less than 1 and modulus of lambda 2 is less than 1. So modulus of 2 minus A is less than 1, and that is minus 1 less than 2 minus A less than 1, that is 1 is less than A less than 3. And modulus of lambda 2 is this modulus of D bracket A minus 1 whole divided by A minus C is less than 1, that is minus 1 less than this less than 1. So for the value of D, after simplification, we can easily get this A into bracket C minus 1 by A minus 1 less than D less than A into bracket 1 plus C by A minus 1, and this is the condition, and hence actually D is this 0, 0 is greater than G and 0 is less than D. So maximum value of 0 and this is less than D less than A into 1 plus C by A minus 1, and this is the condition for asymptotically stable of this steady state U1. This condition 1 less than A less than 3, and second condition is this maximum of this less than D less than this. And third steady state E star. For this E star, this called C1 plus D is called X star, and this point is called Y star. And for feasibility of this E star, that is for existence of E star, we must have A minus 1 by A less than greater than 1 plus C by D. So Jacobian at this point E star, put X star equal to X equal to this and Y equal to this in the Jacobian matrix. So we get 1 minus A by D bracket C minus 1 minus B by D bracket C plus 1 and 1 by B bracket A bracket D minus C minus 1 bracket close minus D 1. Now this trace of this J at the point D star, this plus this, so we get 2 D minus A bracket C plus 1 whole divided by D, and so minus trace of J star equal to this equal to A1 C, and determinant of J at the point D star equal to this into this minus this into this. So after simplification, we get 1 by D bracket A bracket C plus 1 into bracket D minus C minus 2 minus C into D bracket close. This is equal to A2C. Now E star will be asymptotically stable, locally asymptotically stable if modulus of trace J is less than 1 plus determinant of J less than 2. This is the Jury's condition. So trace J is equal to modulus A1 trace J modulus of trace J. So this modulus of A1 is less than 1 plus modulus of A2 determinant J2 is less than 2. So modulus of A1 is this, and 1 plus A2 is this is less than 2, and this is the required condition for locally asymptotically stable of the steady state E star. Note that Jury's condition, actually this Jury's condition is out of syllabus, but this if the characterization P lambda equal to this, where A1 is the minus trace J and A2 is the determinant J, then modulus of lambda 1 and less than 1 and modulus of lambda 2 less than 1, if and only the following three conditions satisfy simultaneously. First condition P1, that is equal to 1 plus A1 plus A2 greater than 0. Number 2, P minus 1 equal to 1 minus A1 plus A2 greater than 0. and number 3 modulus of A2 is less than 1. And after simplification we can get this condition is this. Next question, question part B. Show that the following difference equation xn plus 1 equal to rxn square whole divided by xn square plus a, where a are positive parameters, has 3 distinct steady states if r greater than 2 root a, and discuss their stability. Now putting x comma y in place of xt and xt plus 1 respectively. Actually in the given question this is xn and xn plus 1. So rectify this xn comma xn plus 1 respectively. With the reproduction curve is equal to y equal to rx square by x square plus a. The curve 1 is the reproduction curve meet the line y equal to x at the following points. This. So put y equal to x here. So x equal to rx square by x square plus a. So after simplification we get either x equal to 0 or x equal to this. So the just formula this minus b plus minus root over b square minus 4ac divided by 2a. Now discriminant this r square minus 4a is greater than 0. That is if r is greater than 2 square root of a. Then there are 3 real listing points. So the equilibrium points are given by x1 star equal to 0 and x2 star equal to r minus square root of r square minus 4a by 2 whole divided by 2 and r plus this x3 star square root over r square minus 4a by 2. But if r square minus 4a is less than 0, so this is imaginary. When r is less than 2 root square root of a, then only one real equilibrium point x star equal to 0. Now dy dx equals to this y equal to this. So dy dx equal to this equal to 2r ax by x square plus a whole square. So dy dx at the point 0 0, obviously this equal to 0. Then the x-axis is a tangent to the curve 1 at the origin. X-axis is the tangent to the curve at the origin. Actually this is the curve. X-axis is the tangent to the curve at the origin. Dy dx, because dy dx 0 at this point or at this origin. So the curve will lie below the line y equal to x. Curve below the line y equal to x. This is the line y. This is the line y equal to x. This dotted line. So curve below the line this. Below the line this. Near origin. Also limit extends to infinity y. This is equal to limit extends to infinity rx square whole divided by x square plus a. This is equal to limit extends to infinity r by 1 plus a by x square. This is equal to r. This shows that the line y equal to r is an asymptote of the curve 1. Y equal to r. This is the straight line y equal to r. This is the asymptote of this curve. This is the asymptote of this curve. This. If r is greater than 2 square root a, then all solutions with initial value x0 less than x2 star. So intersecting point. So this first x1 star 0, x2 star this intersecting point, the production curve with the straight line y equal to x. This intersecting point is this. First is this origin, then this, and intersecting point this. Then corresponding x coordinates at the steady state. So x1 star equal to 0, x2 star equal to this value, and x3 star is equal to this. So x1 star actually x1 star equal to 0 and x2 star equal to this r minus root over of r square minus 4a whole divided by 2, and x3 star equal to r plus root over of r square minus 4a by 2 when r square minus 4a is greater than 0. So we get 3 distinct steady states. when r is greater than 2 square root a, then all solutions with initial value x0 less than x2 star tend to x1 star, but the solution with initial value x0 greater than x2 star tend to the point x3 star. When if x0 is less than x2 star, then this by Cobb diagram, this from x0 to this value reproduction curve, then reproduction curve to y equal to x, then y equal to x from this point to reproduction curve, and this, and corresponding this x1, this point is x1 on the x-axis. So the solution x0, x1, x2 so approach to 0, so x1 star is locally asymptotically stable. If x0 starting from the value greater than x2 star, then x2 star to reproduction curve, this from reproduction curve to y equal to x, so corresponding this point is x1 solution, and from this point to vertically upward to the reproduction curve, and reproduction curve to horizontally from this point to y equal to x-axis, and corresponding point on the x-axis is x3. So x0, x1, x2, x3 star, so these solutions close to the point steady state x3 star. So x3 star is locally asymptotically stable, but x2 star is unstable. So solution with initial value x0 is less than x2 star tend to x1 star, but solutions with initial value x0 greater than x2 star tend to the point x3 star. So x1 star, that is equal to 0 origin, is stable, actually locally asymptotically stable, but x2 star is unstable. Also the solutions with initial value x0 greater than x3 star, x0 greater than x3 star, so if we start from this point x0 greater than x3 star, then also this solution move close to the steady state x3 star. Greater than x3 star tend to x3 star, and x3 star is locally asymptotically stable. But if r is less than 2 square root a, then all solutions with positive initial value tend to x1 star equal to 0. So x1 star is locally asymptotically stable equilibrium point when this r is less than 2 square root a. From the second figure, reproduction curve is this, and so intersecting point with this y equal to x and reproduction curve, only intersecting point is origin. So origin is the only steady state, and if we start from this x0, this initial solution, so we get by Cobb diagram to approach to origin. So this x1 star x star equal to 0 is locally asymptotically stable when r is less than 2 square root a. We draw the Cobb figures for both the cases in the next page. So this is the figure for this case, r less than 2 square root a, and just rectify this, in place of xt write here xn or x-axis, and xt plus 1 write either xn plus 1 or y-axis here. So this curve is y equal to this, so put here y-axis and put his x-axis here, this graph. Thank you for watching this video. This completes the solution of Unit 3 2023.